Welcome back, Data Junkies. Hello, how are you? Glad to see you again. I'm your host, Shawn Janzen, and we're continuing our talk on multiple linear regression. And now we're going to advance what we talked about a little bit before when we talked about indicator variables and a little bit about dummy variables. And now we're really going to open up the floodgates to see how they can work and do their magic in multiple linear regression. So we're going to use this with a two-part video series. The first one, I'm going to introduce the sort of foundations here and how they work, with talking you through a couple examples, a little bit from Harry Potter and some Quidditch. So I wanted to give a quick shout out to my spring class of 2018 that gave me this fly-ass Ravenclaw tie, because apparently I used one too many examples from the wizarding world in class, and they thought I was some giant Harry Potter nerd. Kinda am. They hit that one on the head. But yeah, just a quick shout out. Thanks, guys. And I'm going to follow up with another video where we start to see how this works in R with a couple practical examples. So let's go ahead and get started with a talk on dummy variables and this thing called the reference group. So just to recap a little bit, what we know about using categorical variables in regression so far is that we can do it. It's okay that we can do it with the ordinal variables that have 5 or more categories. We're going to sneak them through under the radar as if they were interval or ratio. And when we do so, we just have to keep in mind the interpretations change a little bit. Instead of talking about a 1 unit change, like miles per gallon of gas or seconds on the clock, in that case, we're talking about rank changes, group changes. So if you have a Likert scale, we're talking about as you move from one group to another on the Likert scale. Or if you're talking about income categories, you're saying as I go through one rank of income or one categorical group of income to the next. Okay, and this is going to hold true if you use the categorical with a high number of ordinal categories, either as the independent variable or the dependent variable. Okay, and if you have ordinals for both, then what you're saying is a rank change on one causes a rank change on the other, or corresponds to. We don't want to say causes, but it corresponds to an average rank change in the other. And when we're talking about these binary variables, we're talking about ones that are naturally binary. These sorts of up, down, left, right, A, B only sorts of things. And we call those indicators. And they could also not be binary if we've coded them to be this way as well. So any indicator variable is when we generally like to code it as 0, 1. It doesn't have to be coded as 0, 1. It could be 1, 2, 10, 11, 20, 31, 95, 96. I think you get the point. In fact, they don't even have to be one number unit across. They could be 10 units across, 20 units across, 20 to 40, as long as you have 2 categories in their number coding. Now, the caveat to that is if you have a binary variable, an indicator type variable here, and their coding is more than a unit apart from each other, numerically speaking, it's going to make the coefficients different than if it was only a 1 number difference, and that's okay. It'll wash itself out in the end when you get to the predicted values. But generally speaking, and the software is going to set it up normally for you. If you're doing recoding, try to stick to this as well. Keep them 1 number apart. Now, back to the regularly scheduled topic here, off my tangent, that binary dichotomous variables are these 0, 1 sorts of things, where 1 is going to have the presence of whatever it is that you're talking about, that group of interest, and 0 is the group of non-interest, or in the case of the naturally recording ones, like a yes, no, true, false sort of thing, then it's just simply the other group. Not necessarily saying that you're not interested in it, it's just the secondary group in this case. And when we're dealing with this in a coding presence, when the value is the 1, then you are seeing the effect of the coefficients effect on that particular high coded group. When it is 0 or the low code, if it's not a 0, like if it's a 1, 2 coding, then that group does not receive the coefficients effect. So you interpret those as the higher code receives the coefficients average effect, the low code does not, and you're comparing these two. That's the basis of the indicator variables here. Now, I like the 0, 1 when possible, because if we're trying to figure out these predicted values, then it makes our math really easy. So I have on the screen just sort of a default regression equation, and we could have 3 generic x variables here, and they could be different values. The center one is a 0, 1 indicator. I plug in a 0 for it. That's going to cancel out against its coefficient. It's going to collapse down, and that's 1 less value I have to worry about multiplying and adding in along the rest. So let's go ahead and see how this might work just in a quick practical example here. And I'm going to be looking to predict the number of Facebook friends. And I have 4 predictor variables here, and I have B1, X1, B2, X2, B3, X3, B4, X4. These are going to correspond to 4 variables. 1 is an indicator of if you are female. So 1 is if you're female, 0 is if you're male. Or if we were being a little bit more diverse with our gender options, 1 would be female, 0 would be other than female. Friend of a friend is another indicator variable. So 1 if somebody is a friend of someone's friend, 0 if they are not. The third one is bad reputation. 1 if this person has a bad reputation or not. 1 has a bad reputation, 0 means they do not. And prosocial, 1 means this person's a prosocial individual, 0 if they're not. So we would set up a regression equation that would have a y-hat, a predicted value of the number of Facebook friends. We have our y-intercept, and then where those x's were, I'm going to plug in the names of our indicator variables here. So we have female, FOIF for friend of a friend, bad rep for bad reputation, and prosocial. I could then go ahead and replace those betas with our regression coefficients. And so that leaves us with a default regression equation where all we would need to do then is obtain the values for each particular variable in order to find out the average number of Facebook friends. So using just a brief example, we could look at somebody who happens to identify as male, that is a friend of someone's friend, has a bad reputation, and is not prosocial. How many Facebook friends might this person have given the regression coefficients that we had before? So the first few lines are the same ones from the previous slide. And I'm going to then say, all right, the female variable, this person says they are male, so that's an indicator of 0. I move on to the next one. Friend of a friend, this person is a friend of a friend, so we code it as a 1. This person has a bad reputation, so we code that as a 1. And this person is not prosocial, so we code it as 0. Once I have those values into the regression equation, I'm going to go ahead and cancel out the ones that list as 0. They will cancel out. My numbers will collapse down, and then all I have to do is some basic math. Having them coded at a value 1 is very nice to multiply against my regression coefficient. Very little math to do. So then I just add and subtract across, and I would have a predicted value of 118 Facebook friends for this particular person. Again, it would change depending on the characteristics of other individuals that we would want to predict for. Easy, huh? Well, let's move on now that we've just did a little recap on indicator variables and come back to this idea of dummy variables. Now, we said before that you can use these high category ordinals, that's 5 or more levels, and as the interratio. But the dummies are when we have less than 5 and any of our nominals. Any of our nominals. You cannot use either of these groups in a regression as is. The reason we don't use the low category ordinals is that there's really not enough variation in the number of response categories, number of groups, to really give it a strong amount of variation that you can say as I go from group to group to group. And nominals lack rank order completely, which is why we can never use them as is. And so what we have to do is recode these into dummy variables. Now, we said these dummy variables are these sorts of indicator variables. We're just making many of them. And you can make at most one dummy variable for k, where k is equal to the number of categories in your ordinal nominal variable. Now, I'm going to flip back and forth sometimes between dummy and indicator. They're really the same thing. They operate on the same principle. They are synonymous terms. We just generally only use the term dummy variables when we take a variable that has many categories and we're making several indicators from it. We're usually speaking indicators as a standalone variable. So, when we're doing these particular dummies and we're plugging them into regression, you can have up to k categories, but when we put them into the regression, we leave one of them out. Okay, the one we leave out serves as what we call a reference group. It is a common comparison category to which all of the other dummies we put into the regression will compare to. So think of this when we had an indicator, let's just say male-female in the previous regression, and you'd get a coefficients change if you were female compared to being male. When you're doing this with dummies, you would have several dummies for the different variables you're looking at, and you are going to have for that particular dummy a coefficients change as it's compared to the reference group. All right? Let's go ahead and see how we can choose some of these dummies. Now, if you're doing some of these high category groups, you could have several dummies coming out of them. So how do we know which one to make as the reference group? Well, we have a few strategies in which we can use. First off, We could have the ones that's just interesting to compare to. They're the ones that have some common value that we want to compare across to all of the other groups. So we'll choose to make that one our reference. More commonly speaking, and the one I generally recommend, is use the one that has the largest category. This is going to help you when it comes to things like collinearity and a bunch of other things that we're going to talk about later, and it gives you the best opportunity to get your accurate p-values. So the third one we can choose is comparing against some sort of mean or median. So this is if you have different categorical groups and maybe you've split them, it's a numerical range and you've split them up by categorical groups, and you can compare it against a common group. A mode would also be a good one to use in this case here as well. And the last option is just letting R decide. In the default settings I'm going to show you later, is that what it's going to do is if you put in a factor or categorical group here, it's going to grab the first category in that coded process and make that the reference group. We'll see what I mean in just a moment. So let's go ahead and do a brief walkthrough of an example. This isn't an R, this is just a fun little made-up case in which we're going to be looking at Harry Potter Quidditch games. Well, sorry, not Harry Potter, the world of Harry Potter, and using Quidditch matches. So in this particular case at the Hogwarts, there are the 4 houses that the students can go into: Hufflepuff, Slytherin, Ravenclaw, and Gryffindor. And each of these houses has their own little Quidditch team. For those that aren't familiar with the world of Hogwarts and Harry Potter and all that good stuff, these are little wizards and witches that ride around on their broomsticks, and this is the sport that they play. And so what we're going to use is just an example to kind of predict how many points on average each of these 4 house teams might score. So on the left side of the slide screen here, I have regression coefficients we would have obtained from a regression, where we have an intercept value, and I have 2 variables. The first major variable is what house the students are in. The second variable is the average number of years spent at the school on that team. Okay? So we have a group of coefficients for each. You're going to note that I have 3 dummy variables in there for the houses. This is because we've left one of them out for each house to compare back to. And so what we have is Gryffindor has been left out as the reference group. So each Hogwarts house is going to compare its coefficient value on average back to Gryffindor. And I also put in here an average number of student years that they could spend at school. These range from 1 to 7. And you can be at Hogwarts for up to 7 years. So what we have here in this case is the average number of student years for the Hufflepuff team is 4, 5 years on average for the Slytherin team, 3 years for the Ravenclaw, and 4 years for Gryffindor. So let's go ahead and see how might these go ahead and plug in. Well, I'm going to create 4 different regression equations predicting 1 for each of the 4 houses. They share a common regression intercept. They all, in this case, I'm putting in the dummies for all the houses together, and then I'm going to put in the coefficient for the average student years on the team. Then for each regression equation, I will put in the values that correspond for that particular house. Looking at Hufflepuff, it's going to have the 8 is the y-intercept, minus 1.6 times 1, because this is the house for the Hufflepuff. Slytherins will be 0, and Ravenclaws will be 0, because those indicators, those light switches, are down, showing that they are not part of the Slytherin or Ravenclaw houses. And Gryffindors, they're not going to be modeled in this particular regression equation, so we don't have to worry about that. The Hufflepuffs had an average of 4 years, so that's where they're at. We're going to repeat that process, putting in the values for Slytherin, Ravenclaw, and Gryffindor respectively. Slytherins are going to have 0 on the Hufflepuff variable, 1 on Slytherin, that's the light switch turning on for Slytherin, and light switch turning back off down to 0 for Ravenclaw for the 3 house values. And then they're going to have their 5 in for their average student years on the team. Ravenclaws, they're going to be 0, 0, 1 as we go across the 3 house variables. Indicator switches are down, down, and up for for Hufflepuff, Slytherin, and Ravenclaw coefficients. And then it's going to be 3 for the average student years on the team. The last one, when we get to the Gryffindors, you see the effect, the coefficients changing effect for the Gryffindors when all of the indicators for all these dummy variables for the Hogwarts houses are 0 when they're down. So when it's down at 0 for Hufflepuff, down at 0 for Slytherin, down at 0 for Ravenclaw, then we see the emergence of the Gryffindor effect come in here. And then we see an average of 4 for the average student years on the team. Now, if it seems a little odd, and you're saying to yourself, well, why does it make sense that if I balance all the dummies out at 0, I'm going to see the effect of the Gryffindors come out? The reason is the y-intercept coefficient there. That is a balancer. And what you would find is if you were to change out and redo these regressions over and over and over again, and take a different house each time you do it, the coefficients are going to change for the 3 dummy variables that are in there as they compare back to the reference group that's been left out. But also what's going to change is the y-intercept value as it goes in response to the coefficients that are changing for the Hogwarts houses. So if you were to go through these iteratively and do all the predictions with different reference groups, they'll come out to the same values every time. But let's go ahead and return back to the example here. Go ahead and pause the video for a moment and try to calculate out the Quidditch scores for each Hogwarts house. Okay, so the first step you should have done is canceling out all of those zeros, and then we'll go ahead and collapse them down, and what we should obtain is a Hufflepuff predicted score of 14.4, Slytherin's score of 19.4 on average, Ravenclaw's at 11.8, and Gryffindor's at an even 16 predicted. So let's go ahead and make this a little more complicated. We're going to take the exact same setup we had before with the Hogwarts houses and the average student years on their team, and we're going to introduce another nominal variable that's going to be dummied out here. So we're adding in a third variable group called Brooms. And of these brooms, these are the brooms that the witches and wizards ride around on to play that game, and there could be up to 3 different types. The team could have predominantly old brooms, the team could have predominantly new brooms, and the team could have a mixture of old and new brooms. The idea behind this is that old brooms aren't going to perform as well as new brooms, and so they're going to be harder to move, they're not going to be as fast on the field, and things like this. So we're going to plug 2 out of the 3 groups here into the equation. And so I'm choosing to put in old brooms and new brooms, and I'm going to compare them to the reference group of mixed brooms. When I put the Hogwarts houses in, I'm putting in 3 houses again and leaving 1 back. I'm going to leave Gryffindor back again as well. You may notice that some of the coefficients have changed. Some are relatively the same, some changed a little bit more. This is natural when you get into multiple regression and you're redoing your models, adding in or taking out variables. Some coefficients may change in response to others going into the model because of part of the variation that could be shared between variables that has been explained by introducing others. So if we were to go ahead and plug some of these in, here is our full regression model here with our dummy variables. Again, Gryffindor and mixed brooms are our 2 reference groups. Every categorical variable you put in there that has dummy variables is going to have a reference group, and you may have 3, 4, 5, 20 different reference groups, 1 for each of these variables that have been dummied out, and you're only comparing them back, those dummies back to their reference group. We're not going to compare the old brooms dummy to Hufflepuff, for example. Only compare it back to their mixed brooms category. So go ahead and take these regression coefficients, take the average student years, and try to predict the 3 scores for the broom differences as they apply to the Slytherin house and the Gryffindor house. Okay, so you're going to do a total of 6 predictions, 3 of the broom types for Slytherin, 3 of the broom types for Gryffindor. Pause the video, see if you can do the calculations, and then we'll come back together. All right, so, and here we have the 6 predicted values here. I have them split into 2 sides with the Slytherins on the left, Gryffindors on the right. Old brooms are calculated up on the top, new brooms are in the middle, and the mixed brooms are at the bottom. So what we're going to do here in this case is we're going to go look at the first upper top left and see how the Slytherins with old brooms would predict. So they're going to have the y-intercept of 7. We're going to plug 0 in for Hufflepuff, 1 in for Slytherin, 0 in for Ravenclaw. The ones with the zeros will cancel out. The average student years was 1.7. Slytherins had 5 years on average for their team. And then we're going to have the regression coefficient for the old brooms was negative 3.1. That indicator is going to turn on because we're doing the old brooms estimate. Then the coefficient for new brooms. Well, if we're using the old brooms, we're not using the new brooms, so that's 0. So what we're going to have here is the zeros are going to cancel out. We're going to add up what's across after we multiply, and we're going to get a predicted amount for the Slytherins with old brooms at 14.1. Looking down at the new brooms, we have the coefficient of 7. The coefficient of 7 is going to be the same for all of the groups that we're looking at. So then we have the 3 house coefficients, Hufflepuff, Slytherin, and Ravenclaw. Again, the indicators are going to go in as 0, 1, and 0 respectively. The average house years is 5. Then we get to the 2 coefficient dummies for the for the broom use. We have old broom indicator is off, new broom dummy indicator is on as it's compared to mixed brooms, and we get a predicted average of 21.4 Quidditch points. And then we get down to the bottom where we have the Slytherin mixed, and we have the same house indicator dummies up there. We have the same student years. And then when we get to the brooms, both old broom and new broom coefficients are 0. When they are 0, the effect of the reference group emerges. And this is where we're going to see the effect as it's built into the y-intercept of the mixed brooms. Now, I said before that this is when the reference group effect emerges. So that 7 captures both the amounts coming off of the reference group for the brooms and Gryffindors, although we don't see the Gryffindor effect in this particular predicted equation because we have the Slytherin house coefficient activated at 1. It might take you a few tries to get your head wrapped around this, but don't worry. I have faith in you, and I trust that we'll get it. And if you're still confused, please come see me. I'm more than happy to help you walk through these. So looking on the right, we have the Gryffindor teams, and we're going to repeat that process for old, new, and mixed brooms. Up at the top, we have the Gryffindors. The zeros are going to cancel out for all 3 houses because we're looking at the Gryffindors. Then we're going to have the new broom coefficient at 0, the old broom coefficient at 1. The new broom coefficient will cancel out. In the new brooms, in the middle there, we have, again, the 3 houses are zeros. They all cancel out because we're looking at the Gryffindors. The old broom coefficient cancels out. The new broom coefficient is active because we're predicting the new brooms. Then when we get to the mixed brooms, again, we're going to cancel out all of the houses. We're going to have both old and new broom coefficients cancel out at 0, and we're going to see how those go. I've got one more slide where I just kind of clean things up a little bit, and we can see how each of those are playing out. And I've put in red there the coefficients changes for each of these as they appear on the brooms. Now, what we're looking at here also in the red are the predicted scores. And so what we would generally see is if we had believed that old brooms were going to have less of a benefit on the team and the new brooms are going to give more of a benefit on the team, we see that in the predicted point spreads. For both Slytherin and Gryffindor, they score fewer points predicted on average with their old brooms, the most with their new brooms, and the mixed brooms are somewhat in between, respective for each group. And so this is sort of how we're dealing with each of these particular groups here. If we're going to have just some more practice to kind of interpret some of these coefficients, if I was to look at the Slytherin old brooms, that would say that Slytherins using old brooms are going to score 3.1 points, Quidditch points, on average less than Slytherins using mixed brooms. The second one would have a plus 4.2. I would say that Slytherins using new brooms are going to score on average 4.2 Quidditch points more than a Slytherin team using mixed brooms. And if we were to look at the Gryffindor side, we would say that Gryffindors are going to score 4.2 points on average more than Gryffindors using mixed brooms. And so there we go. I'm going to go ahead and wrap up this video here. So I'm going to see you all on the next one where we're going to see this with, using live data, and we're going to do our regressions in R. I'll see you then.